Shcherbina from Princeton. She will be speaking about universality of the second mixed moment of the characteristic polynomials of the one-dimensional Gaussian band matrices.
So first of all, I would like to thank the organizers for invitation. Yes, I have it. It's fine, yes. So I would like to thank the organizer for the invitation for this conference. It's a big pleasure for me. And also I'm very grateful to Leonid Andreevich, who comes to this auditorium and who was my advisor during my PhD, and I wish him many, many years of effective work. So let us start. I'll speak about the random 1D Gaussian random band matrices. We heard a lot about these matrices during this week, but I briefly say the definition to fix the notation. So we consider the Hermitian Gaussian 2n plus 1 times 2n plus 1 matrices Hn. So I enumerate indices from -n to n. And the elements of these matrices are Gaussian with mean 0, and covariance of such pair is Jij. Jij supposed to be small for big difference between n and j. Here we take the special convenient choice of j, which is given by the lattice green function. We can see the definition here. Here, delta is the discrete Laplacian here. Note that for this choice of j, jj has such order, and so if the difference between I and j much bigger than w, then the variance is exponentially small, and so w can be considered as the weight of this band. Where is the page down? Denoted by lambda the eigenvalues of random matrix, and the first question that's usually asked in a random matrix theory is the convergence of the normalizing countermeasure. This question for this ensemble was done by Molchanov, Pastor, Harunji in 1992. It was proved that the normalizing countermeasure is converges, and the limit is semicircle law, Wigner's semicircle law, so it's very famous. This is the first question of so-called global regime of the random matrix theory. So we consider the behavior of eigenvalues on the interval of the finite length. The other interesting regime of the random matrix theory is so-called local regime, when we consider the behavior of the eigenvalues on the intervals whose length is of order the mean distance between the eigenvalue. The main object of local regime is the k-point correlation function that can be usually considered if we obtained if we take the joint eigenvalue probability density and then integrate each over the last n minus k variables. The most interesting question in the local regime is the universality conjecture for the correlation function. There are many types of universality, and there are many types of formulating the universality, but we formulate universality for the Hermitian Wigner matrices in the bulk of the spectrum. So the conjecture says, it was conjectured by Dyson in early 70s, I think, and the conjecture says that if we take the correlation function for all lambdas that lies in the 1 divided by n neighborhood of the point in the bulk of the spectrum and divide it by some factors, then in the limit we obtain the sign kernel. And this behavior is universal, so we obtain such limit for all Hermitian matrices, and it is independent of the ensemble, the probability measure on the ensemble. This conjecture was proved by many different cases. For example, for many cases in random matrix model. In the recent work of Erdős, Jausch, Lane, and Tao Wu, it was proved for the Wigner matrices and for the Hermitian matrices, Hermitian Wigner matrices and sample covariance matrices in some constraint, but it's not important. But for random band matrices, it's not so much result. We heard a talk yesterday about this. And also there are some results on the edge of the spectrum, the universality. There are other kernel, and there are results of Sasha Sodin in the edge. But in the bulk, there are not so many results. Here we consider the questions that closely connect with this one, but much simpler technically. We heard in the, so we consider the creation function of the characteristic polynomials. We heard in the talk of John Keating that this question have many connections with other branches of math, and so this question is of independent interest. And so we consider the two determinant and take the averaging on the probability measure of this determinant. And again, we are interested in the asymptotic behavior of this function for lambda that y in the neighborhood of order 1 divided by n. For Gaussian unit ensemble, that is for the matrices with Gaussian independent elements with mean 0 and y-ons 1, this asymptotic behavior is well known. It's obtained that, again, if we take 2k point correlation function, that is 2k determinant, and take in the bulk of the spectrum and take some normalizing factor, then the behavior is like this. So we obtain some constant here. It's a multivariable constant, and then we obtain the sign kernel again, but this is not like the previous sign kernel. The kernel is the same, but the determinant is different. Here we obtain the pairing of oak size, and here it's a little strange determinant. So we have two cake size. We divide it by two parts, equal parts, cake size and other cake size. We form this determinant from the other. We take one psi from one group and one psi for another group, and then we divide by the van der Waals determinant of each group. This function seems not symmetrical in Xi, but it is symmetrical in Xi, and it should be because this function is of course symmetrical in Xi. And this behavior is also universal, conjectured to be universal for the Hermitian matrices. So it was proved the same result for the Hermitian matrix model. It was proved by Byzantine and Fedorov-Strachov. And the same result was proved for Hermitian-Wigner and general sample covariant matrices. It was proved for k equal to by Goetz and Kosters, and for other k by me. So the main result. We heard yesterday that in the random matrices, 1D random matrices, there is a conjecture that we have the phase transition, and the conjecture that the critical value is w equal to square root of n. So the conjecture says that if w grows faster than square root of n, then we obtain the behavior like in Gaussian unitary ensemble. So it's that called the extended space. And if w grows slower than square root of n, then the behavior we obtain the Poisson. Here we consider only first part of this conjecture. So we consider w that grows faster than square root of n. So in this assumption, we prove that the limit with some, this is some normalizing factor, it's not important, that the limit of the second correlation function of the characteristic polynomials with this assumption is sine kernel. How we prove this result? There are always two steps. First step, we obtain the convenient integral representation. And the second step is to apply the steep disk method to this representation. First step here is simple, because he is very standard. We use the Grassmann variables to obtain this representation. I don't speak a lot about the Grassmann variable because I think that most people will know this method. So I recall only that we can represent the determinant in such form. Then, of course, since we have two determinants, we can use this formula for each one. Then we obtain this representation, collect the term near the independent random variables, because real part and imaginary part of H are independent. Then we doing the Gaussian integration over the probability measure. And then we obtain such term. Again, by the standard way, here we obtain the fourth term on psi, and so we use the Haber-Satanovich transform to obtain the second term of psi. After this, we can integrate out of the Grassmann variables, and then we obtain such integral representation. Note that there are no Grassmann here now. There are only matrices XA. XA is Hermitian 2 by 2 matrices. That is expectation integration over all this xj. And here we can see such things that in the Margarita Stokes yesterday. So it's like a spin we have here, this matrices xj, and this is interaction between the adjacent xj. To apply the steepened descent method, we should diagonalize this xj. So we are going to do the change of variables. Then the Jacobian of this change is Vandermonde square. And this term is unity invariant after this change. This term, this part of this term is also unity invariant. And so we obtain uj only in this part and near the psi. We want this to be quadratic and unitary group. So the second change that we do is we change uj to some other group matrices of such pair. Then after this change, we obtain the final integral representation. Note that we have two big parameters. One is w and second is n. So this is big. And also this is big because we have the sum from -n to n. This function you can read the definition here. It's of order constant because we have sum, but we have 1 divided by n. So this addition gives a constant and not important for the first part of steepened descent method. So if we put psi equal to 0, so we omit this f, we obtain vj only in this term. This is quadratic on vj, and so we can integrate over it using the Isaacson-Zibert formula, and then we obtain such formula. Note that all this Vandermonde cancels except first one and the last one. And so we obtain, we can see that this integral almost factorized on a and b. And you can see that it's important to study the measure that of a that should be this term and also this f.
What is the f again? I've forgotten what f is.
F is yes, it's terms I can now. Is term this one and log of this determinant. So f is such.
So do you just so you still have you have scalars. You have a's and b's. Those are scalars, right?
A and B always.
They're numbers.
Yes.
For every lattice site, or trying to understand. Yes. And then you're still integrating over the
A and G lies in the real line. It's variables now. the expected saddle point are, when we can see here, it's of course a maximum value of f, oh, maybe minimum value of f because that's minus, and the expected saddle point are, since we have the big parameters here, is when OA equal to this maximum point and minimum point, and OB equal to the maximum point. F has two maximum points. It's A plus and A minus, so the expected saddle points are of this form. So OA is equal, OB equal, and they are equal to plus or minus. And note that also that if we look at this formula, we have this Vandermonde, and so if OA is equal to OB's, then the order is smaller. So the main contribution gives by the points where OA is equal to A plus and OB equal to A minus, and also when different, well, A equal to A minus and B equal to A plus. So the first step is to prove that the main contribution is given by the delta neighborhood of these points. Moreover, we can take delta equal to W in power minus kappa with sufficiently small kappa, positive kappa. The main point of this step is this. Since we have this W square here, we can do big steps between Aj and Aj minus 1. So the steps should be small. And if we do the small step, we can go far because we can do only n of such step, and n smaller than W square. So the next point is to compute integral over the delta neighborhood of this point. So we change variable matrices. So this is eigenvalues. We go to the neighborhood of point A plus A minus. So L is a matrices with diagonal element A plus A minus, and Rj with tilde is a new variables we divide by W, and so we obtain the integral over this set. And here we separate the quadratic term of this measure. Look at again and the expanding of f. This is quadratic term that we have, and all other terms we denote by phi plus minus. The key point here is that this c plus minus, so the coefficient under the quadratic term, is complex. If we have the real coefficient, it will be much better, but we have complex coefficient. And so this measure that we wrote here is not a measure because it's a complex distribution sum. So this gamma is complex, but with positive real part to converge this integral. So we separate here this measure for A and B. This is the part that, as we know, after integration over Vj cancels this Vandermonde. And so our question is what we can do with this term. We want to prove two statements. First statement, that the main contribution of these terms is 1, so that we can omit this term. And the second one is that when we integrate over the unitary group, over the Vj, then we can replace this expectation of this function f. I recall that the function f have this form. then we can replace this term by this term. So we put all a equal to L. So we put all our new variables aj tilde equal to 0 and put all vj equal to I. Then this term becomes equal to this one. So it remains only u minus n, the first unitary matrices. And it is easy to see then when we integrate this over the u minus n using this on the bear, we obtain the sign kernel. So the sign kernel can be obtained from this term. To prove the first step, we should study the measure mu that we write on the previous slide, this one. So we define the expectation over the whole real axis by angle brackets and the expectation over the interval minus delta w by the angles with 0. Also, we define the expectation over the measure with the real part gamma instead of gamma here by the angles with 0. So, first statement is we are going to prove that if we take such exponent minus 1, then the expectation over the complex measure in the delta minus delta w interval is small. Here G is an arbitrary series that started from the third power. First step is to prove this for the positive measure. So we now put here 0 and star and try to prove it for the positive measure. Here we have two ideas. First idea is that we can replace the integral over the neighborhood by the integral over the whole real axis with such arrow, which is sufficiently small. The second idea is that when we come to the all real axis, we can apply the Wick theorem here. So this the Wick theorem, and after when we can, here should be the stars. And when we apply the Wick theorem, we can separate the terms of such expectation of such pairs. Such integral of expectation of such pairs gives the inverse matrix element, where M star is the matrix of such form. It's the matrix that of this measure mu. And we can calculate these elements, and they are of order W. And also, it's very helpful idea that we know that eigenvalues, that this is eigenvalue of this operator, and so we have that sum of these elements are W squared divided by real part. This helps us to, okay, if we consider this sum, if we use this bound to all these terms, we obtain here n times W. And if we have use this equation, we obtain W squared, which much smaller than NW. And recall that all x divided by W. So this term should be CW divided by W square is 1 divided by W. And this term should be, the sum should be like constant. And then after some combinatorial arguments that some computation trees, I don't want to stay at this point, we can obtain this statement for the positive measure. But the main problem here is that we can't easily come from the complex measure to the positive one, because when we try to take the absolute value, we obtain a very big error. This error is of order Cn divided by W. And so we can't do it. And also we can do any estimates with absolute values. And the other problem that we can't go from the integral over the neighborhood to the integral over the whole real axis, because we can't use the absolute values. And so to come from the complex measure to the real measure, we should do something else. So the main idea to do this is the following inequality, which can easily obtain using the Wick theorem. So the absolute value of the average of such x is smaller than expectation over the real measure. This is true because, look at this operator, the averaging over the operator angles is with gamma instead of the real gamma, and m star is with this real gamma. But when we compute this element, so the elements of inverse matrices, we can bound the elements of inverse matrices with gamma by the element, the absolute value of the element ij of the inverse matrices with gamma by the element of the such matrices m star. And so, since this expression vk, using the theorem, we can write like a sum of such m star minus 1 and some elements, then we can write this. So we return to our first statement, this one. We expand this exponent into the series and obtain this one, and then we collect all the elements of the fixed degree. So sigma k0 is the sum of all terms with fixed power. Then for terms with big K, we can take absolute value, and so we take this error, and so then we take the positive measure, and using that we prove our statement for the positive measure, we can prove that the contribution of such terms is small. It's not very surprised, because recall that xj divided by w is small, and so if we have a big degree of such elements, then of course it is small. And for other terms with k smaller than cn divided by w, we can change angles with 0, so the averaging over the neighborhood to the averaging over real axis, and then we can apply this estimate. Then we again go to the positive measure and use the statement that we obtained here. So this statement gives us that we can estimate the averaging of some function over the complex measure by the averaging of some function which is changed. What means change? Change means that we take, instead of Taylor's coefficients, we take the model, absolute value of this coefficient, and obtain the new function. So I try to formulate it more precisely. Define the following partition ordering. Let phi1 and phi2 be two analytic functions, and let the coefficient of the Taylor expansion of phi2 are non-negative. Then we can write that phi2 measurizes phi1 if the absolute value of each coefficient of the Taylor expansion of phi1 does not exceed the corresponding coefficient of phi2. The discussion above yields that if we can measurize this difference by the product of such functions, here q is a series, then we can bound the averaging over the data neighborhood of the complex measure by the averaging over the positive measure over the data neighborhood with a small error. We discussed this for Q that started from the third power, but it is easy to prove that also we can take Q starting from the first power, but we need some constraint to the first two elements. So first element should be smaller than W1 over W, and second element should be small. And then we can such bound, and this can be computed using again the same statement 1 for the positive measure, and can be bounded by this expression. So we prove the first statement and prove such equation. The next step is to integration over Wj. To this end, we again expand this.
What is the Vj?
Vj is a unitary matrices. Now I show you. This one.
So you've been integrating out radial coordinates, is that right, so far?
Yes, I can work with radial, so now I want to work with angular.
Okay, so that's the next step then.
Yes, that's the next step. And we have Vj here. This is our measure over Vj. And we also have Vj in F capital. So we want to expand this Fj capital into the exponent of this F capital into the series over the non-diagonal element of V. V is 2 by 2 matrices, so there are only one element of diagonal. So we can write that. And so we need only one variable. It's this V12 in square. And then we want to prove that only the zero term gives a contribution.
So the zero mode is going to be the dominant contribution.
Yes,
and
yes.
that's responsible for the universalities.
Yes.
The universality, right?
So we want to prove that if we take the exponent, this is AB is A capital, and subtract the F with A equal to 0 and V equal to 1, and then subtract from this exponent 1, and times by this product is this product of such exponent. We want to prove that the expectation over in the neighborhood of these variables is small. Main problem here that our measure of V depend on A also, A and B's. So if we have the measures that are independent of A and V, it's all simple because there are no problems here. But we should control these A's. And first of all, we can control the A's that there in the I recall that F is 1 divided by n, some constant. Here we have the trace, sum of trace, minus n product. This is F, and first of all we want to omit this term. So we use our statements that I formulate before and write that the difference of this expression, this is, I don't know what is this n, can be measured by such expression. Here we have the product, and the first coefficient is small enough because we need 1 divided by w, and we have here such coefficients, not a problem. And so now we should integrate only this part without this aj. But we still have a and measure. I write what is this. We should estimate this difference, the exponent of this difference, and this one can be written in such form here. So let us calculate 2s moment of the expression. This measure is the measure that I wrote this expression here. Now I show you this once more. This one and this. No, without this undermount, only this one. Exponent is this measure. So we can calculate it. This is terms that can be obtained from the Isaacson-Weber, and all other terms for q not equal to j. So this term is from Isaacson-Weber. This van der Monde cancelled by the van der Monde that we have in our integral, and to obtain the 2s moment, we should differentiate this expression for such x. Note that if we differentiate this, then we obtain e in the power minus x, and x is big because a plus minus a minus is some constant, and we have w square here. So if we differentiate this one, we obtain e minus w square on some constant. And so we should differentiate the denominator. But if we differentiate the denominator, we obtain the additional degree of x, and so the additional w square here. Of course, to do it precisely, we need more thin arguments to do it, because the main problem that we have this a's in our measure, and so there are many work here, but the idea is the following. So maybe. Thank you for your attention.
Thank you very much.
You considered the case of a band matrix in one dimension, if I understood it correctly. But presumably you can do a similar analysis in higher dimension. Because the role of W will be somewhat different, but
the main problem there is that I can't use the Isaacson-Weber in higher dimension because I can't obtain the quadratic form in this measure. I try to. Where is it? This one. I can't obtain this quadratic measure because of oops. For example, if I take two-dimensional, I do the change. So I have here the matrix U1, U2, U3. For one-dimensional, I do the change U1, U1, U2, U1 star, and that corresponds to this edge. But for two-dimensional, for example, and also for the dimensional bigger than 2, I have loops. And so if I do such change that corresponds to these edges, I obtain the condition that I should obtain this one. So maybe it can be done, but I don't know. Now I don't know how. So I think that we need some more methods there of statistical mechanics maybe. I don't know how to work with these angle variables.
Other questions?
So we know sort of on the physical level of read how to calculate, for this band matrices, more or less everything as a, the parameter w squared over n, which is the, sort of the main parameter. So now, but you showed that for this quantity where the calculation sort of easier, so you don't need. So we do it, say, for typically by using supersymmetry and supersymmetric sigma model. And I understand that that's something which is difficult from point of view of mathematics. Yeah. So you choose a quantity for which no supersymmetry does not arise because you start from this product of this determinant.
Yes, I understand.
Okay. So now the question is the following. So we know how to calculate things as a for any value of this w squared over n, and for example, in particular, we can be in the limit when this ratio is big. This is your limit, and you show that as a leading approximation, you get sort of randomatic theory.
Yes.
But now we also know, for example, how to calculate corrections to this. So would you be able to calculate corrections to this?
I don't know
leading
now.
error?
I don't know now how to do it. Because we have a difficult sequencing method there, because we have the infinitely many variables, and so it's maybe we can for w squared bigger than n, but I don't know now. I can't answer.
So I mean corrections in this parameter. So you have a parameter which is w squared over n. So inverse of this is a small parameter, and so the question would you?
Maybe the first correction is possible to calculate. The first correction, maybe it is possible, yes. The higher correction is difficult, but the first correction maybe.
One last question. If not, let's think Tatiana again.